All right, we're going to take a look at a pretty challenging question. I think at least in terms of like amount of content, this is a pretty beefy question. So a second order reaction is studied in lab and multiple trials at different temperatures are conducted. All right, so somebody went into lab, they studied it, they figured out it's second order, and they did it at different temperatures, which means that we're looking at that Arrhenius relationship because that's where temperature becomes a variable. So our first question here comes from section 14.3 on integrated rate laws. It asks to determine the rate constant at a specific temperature, researchers should find the slope for the graph of, and then we get a bunch of graph options. Okay, so we have reactant versus time, or concentration of the reactant. The time, we have ln of reactant versus time, 1 over reactant versus time. And then we also have some that are versus temperature. I didn't slouch on the number of options here. K versus temperature, ln of K versus 1 over temp. And I think I have one more. What is it? Okay. Oh, just ln of K versus temperature. Okay. All right. Those are our options for the first two questions. All right. So in the first question, we want to determine the rate constant. We'd like to solve for K using a graph. Okay, so we're not going to do the initial rate method. That's not part of this. This is the supposition in this is that we're going in and we're going to do the graphical method to figure out the rate law. Okay, so the key here is to recognize that this was given to you, the second order reaction, which tells you that we should analyze it using the second order integrated rate law. Okay, second order integrated rate law is 1 over the concentration of our reactant, okay, at any time t, that equals K times T plus 1 over Rx at the initial time point, okay, our initial concentration. Okay, so when we plot 1 over the concentration versus time, notice that this has the same format as a standard linear equation, y equals mx plus b, provided that we plot 1 over our concentration versus time, that's our x, then our slope would be the rate constant. All right, so the answer I'm looking for in this question is 1 over our x concentration versus time. Okay, don't get distracted by those others that have k. We're solving for K. We need K before we can move on to do anything else with it. And so we don't have Ks yet in this sort of imaginary situation. This would be the first step of like, hey, I need to find K for all these different temperatures that I'm investigating. So I need a second order integrated rate law to do that. And we're looking for the linear graph of that. The next question has the same list of options, but it's to determine the activation energy of the reaction. Researchers should find the slope for the graph of, and here we're looking for the natural log transformed Arrhenius equation. So how we would typically do this, we know that K equals A times E to the negative EA divided by RT. We're trying to solve out for this. What we were told up here is that we're finding K at different temperatures. All right, so we've run this at a bunch of different temperatures, all right, whatever the second order reaction is, and we've measured K at each one of those. So we have a set of data relating K to temperature, all right, but this graph, the Arrhenius graph, if I were to just plot this, looks like that, okay? It's an exponential. No one likes to work with an exponential. So instead, what we do is in the same way that we did this up here, or very similar, we're gonna up there, I mean, when we're thinking about our integrated rate laws, we're gonna be clever and we're gonna take the natural log of both sides. Okay, because I don't want to deal with this E anymore. E's are not mathematically friendly. So what I'm going to do is knock that out. So I have ln of k equals ln of a plus the natural log of e to the negative ea divided by RT. What I've done from this step to that step is use my log rule, that the natural log of a times b is equal to ln of a plus the ln of b. Okay, so that just allows me to split up this product into two terms. This stays as it is, but the ln of e to the x equals x. So that's how I get to bring down this stuff up here and drop my x. So I'm going to have the natural log of k equals the natural log of a, which I don't think I've said it out loud. That's my frequency factor, plus, well, I guess we could say minus EA over R times 1 over T. And the reason I wrote it like this is because this is the variable we've been changing, and this is the variable we've been monitoring. So again, if we can be clever and say, hey, I see that if I plot the natural log of K as my Y as a function of 1 over T as 1 over temperature, I will have a linear graph, and my slope will be M, that's my slope, equals negative EA over R. Okay, so if I find the slope of this graph, I'm one step away from determining the activation energy. I just need to multiply it by R, by a negative R. So EA equals the negative slope of that graph times R. All right, so the answer I'm looking for here was this ln of K versus 1 over T. And that big T is for temp. Okay, lastly, if the reaction has a rate constant of 0.533 inverse molar inverse seconds at 25 degrees Celsius, and the researchers determined that the activation energy is 77 kilojoules per mole, what is the rate constant at 40 degrees Celsius? So this is why this is such a beefy question. So I just asked you two pretty complex graphical questions, and now I'm asking you to do a pretty complex calculation. So if you feel comfortable with this, I think you should feel good about how ready you are for the exam. Here, what information are we getting? We have, might write this down. I have K1, so I have some K at a temperature, right? I compare those two. And then I have EA, and I have the second temperature, right? I'm asking about 40 degrees Celsius. And the thing I'd like to solve for is the new rate constant at that temperature, okay? And so I would, on the exam, if I got this question and I was feeling overwhelmed by it, I would go to my equation sheet and say, okay, what equation can I use? Or what equation on that sheet has these four like variables and this? And you would find the 2-point Arrhenius equation. So that's ln of K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. And that is an equation, you have that, okay? So that's given to you. You just need to notice that you have 4 of the 5 variables. Okay, so let's start plugging things in. So I've got ln of 0.533 over K2. That's what I'm solving for. I have 77 kilojoules per mole as my activation energy. I'm going to write that as joules per mole because R, my gas constant, is in joules. So you got to make sure that those are in the same units. So 77,000 joules per mole. R is 8.314 joules per mole Kelvin. All right. And then I have 1 over my second temperature. And remember that we need this to be, notice I just wrote my units for R, and that was in K as in Kelvin. So I need to have Kelvin too. So I'm going to grab my second temperature. So it's my 313, so 40 plus 273. And then 25 plus 273 is my initial temperature. So that's 298. So just make sure that you pair these appropriately, okay? That you got to have them matched up. Otherwise, you're going to get a funky answer. All right, so now I'm just going to start plugging in. I'm being very careful with my calculator punches. This is, I think, a pretty easy place to make a mistake. Okay, so that's my first, that's this right here. And then I'm going to have it by 1 divided by 313 minus 1 divided 298. Okay, so that's negative 1.608 times 10 to the negative fourth. And this is out in Kelvin, and this is in 1 over Kelvin. So now I'm going to get something that's unitless, which is good because I have I'm unitless on my other side. So units are checking out. So I'm going to do 9261.5 times that negative 1.608 times 10 to the negative fourth. That got me negative 1.489. All right, that's now unitless. That equals the natural log of 0.533 divided by K2. Right, I'm going to bring both sides to E so I can get rid of that natural log. So I'll have 0.533 divided by K2. This is in its rate constant units. We're also going to get that for K2. So E, I got 0.2255 over here. And now to solve for K2, I have 0.533, 1 over molar seconds, divided by 0.2255. Oops. Okay, I got 2.36. All right, and let me just like double check that that was in fact an answer. I have a 2.37, which is pretty darn close. So that's what that's what I was looking for there. I will recommend at this point to stop and ask yourself, does that number make sense? You just did a lot of calculator punching and algebra. Make sure that you come up with an answer that makes sense. So how do I decide if this makes sense? Well, it said that at 25 degrees Celsius, I had a 0.533 rate constant. All right, I'm increasing the temperature. I should see an increase in this number. Okay, so, and I've increased it by 15 degrees. So probably on the order of like doubling, maybe tripling. And we are in a reasonable number here. So if you actually go and look at the options, 3 of them can be immediate. There's 5 options on this dropdown. 3 of them can be immediately removed because they're either equal to or less than that K1 rate constant. And you know the rate constant has to get bigger. So there's only 2 options that make sense that are actually bigger than 0.533. So right away on the exam, you could take it from a 5-option question to a 2-option question really quickly. So if you needed to make a guess because you were running out of time, you give yourself a 50-50 chance. So look for those areas or options when you're going through the exam where you can like strengthen your odds by just using a little bit of common sense and checking in with reality before you dive into the math.